To talk about how social networks evolve. So let's do that. First, a few seconds of respect for the Ukrainians who are still fighting. As soon as they stop, I will not show this anymore. But it's still going on. So a few seconds of respect for them. Okay. Today we're going to talk about social networks. So last week we started already. It's a graph where you have people are the nodes, and you link when there's friends, and you can have strong or weak links if there's close friends or just acquaintances. And we're going to see how that evolves over time. Because the internet is always changing, never the same. So it's really important to imagine that it's never fixed. And so we're always going to be talking about something which is moving, evolving. Last week we saw triadic closure. This is a mechanism when you have two people who have a common friend, they tend to become friends. So triadic means it's like a triangle that closes the triangle. Right? So that's a kind of evolution. So that means more and more people tend to become friends. And that's what we're going to study today. All the different ways that social networks are evolving, and you will get a lot of intuition, but also very precise information. First, I'll talk about similarity between friends. Why do people become friends? So it's kind of sociology. So part of the course today is sociology. And this is there's a principle called homophily. This is coming from psychology. We make friends with people who are similar to us. It's very logical. And there's two ways to do that: selection and social influence. Selection is internal. I decide I want to be friends with somebody. Or we have social influence. It's like peer pressure. That somehow the external world forces me or makes me do it. Okay, so there's internal and external. And then we'll talk about why people become friends. And so we will extend the network. We will add nodes called focus nodes. And these focus nodes will be like clubs or interests or anything that people can, that makes them individuals, it makes them similar. And so into the network, we add these new kinds of nodes. They could be clubs, for example, chess club or karate club. And once you do that, you have new kinds of closure, not just triadic, but also the other ones, which we will talk about, focal membership. And then we will do some empirical study, not just theory. We see how it actually really works. So for networks of friends, people exchanging emails, there's a famous Consonants and Watts studies. There's also studies of a system called LiveJournal and Wikipedia. So we'll really understand how it works, this evolution. Also comparing the peer pressure and the internal. The selection of social influence is kind of hard to understand because it's kind of in your head. So how can you compare it? It's not easy. But there was a study that actually is able to compare that. And finally, we talk about friend-enemy networks, where the networks have also negative links. Enemies, not just friends. And then you also have evolution, but it changes. You can have groups of enemies. Like two groups, each group is friends, but they're enemies. Or many groups of enemies. And in politics, it happens a lot. And there's also evolution. And it's called structural balance. So this also evolution with the friends and the enemies. So that's kind of what we're going to talk about. Let me summarize the whole lecture in one slide. This is a new slide which is not yet on the Moodle, which I added just today. I tried to make it the whole lecture kind of very intuitive. So there's 4 ways that we're going to study that social networks evolve. So the first way, so there's the 4 areas. The first way is triadic closure. Friends of friends become friends. But then we add this focus nodes. We get social affiliation networks so we can be more precise. People become friends because they're both interested in role-playing games, for example. So they both join a group of role-playing games and they become friends. This is called focal closure. They become friends because they have a common focus. And so that's the second way that we're going to see it evolving. It's more precise. The third way is with enemies. Okay, I have to introduce some notation. So here you have 3 people. The plus means they're friends. The minus means they're enemies. So B and C are friends, but they have common enemy, A. They both hate A's guts. Okay. That's okay, it happens, right? So you can have networks where everybody is friends. So this is plus, minus, minus. So 2 friends with common enemy, but maybe everybody is friends. And that's called strong balance. Strong balance is either everybody friends or they're friends with common enemies. And if you have that, you also have evolution. And you basically have 2 enemy groups are going to form. So we'll show that. And the final one is where you allow everybody to be enemy. You allow A, B, and C to be really, each one hates both of them. So that's minus, minus, minus. If you allow that, sometimes it happens in politics, geopolitics, whatever, or Tour de France. They're not really enemies, but each team is fighting against all the other teams, right? So you have many enemies. And if you have this, you will have N enemy groups that are forming, and not just 2. Okay, this arrow should be a little bit lower. N enemy groups. These 2 should be a little bit lower. Sorry, I have to fix it. So these are 4 kinds of evolution that really happen and let you understand how the internet evolves. Okay? So this summarizes the things we see today. First, I want to talk about friends in the social network. Friends are kind of like each other. So this is a sociology course now. This is called homophily. You can look it up on Wikipedia. There's also a more complicated word used for this, assortative mixing, but it means the same thing. It means that friends kind of are like each other. Okay? And how does that work? Well, it can be different ways that they're similar. They can be similar because they're both in the same ethnic group, or they're both in the same age group, or something like that. It doesn't change. Or they can be mutable. Maybe they're both very poor, very rich. Maybe they're both loving computer science, or philosophy, or whatever. So you have many different ways people can be similar. But I want to show you some examples. Here's a nice graph. This is typical American. Okay, so this book was written by 2 Americans. So you can see the examples were very American. So this is students in a high school in an American town, secondary school. You can see there's 4 pieces. So each of the nodes is a person. The color depends on the race, so probably white or black. But in order to be neutral, they have a yellow and green. And there's a third one, which is red. Maybe those are Asian Americans, I don't know. And then you have the age, is the other division. So the middle school and the high school, what's in French called collège and lycée, so which also meant to separate you. So you can see they're kind of 4 graphs that are connected to each other. 4 densely connected, homogeneous parts that are weakly connected to each other. So that's an example. Huh? You see how the similarity makes difference. Okay. Here's another example. This one it also has to do with race. You see, Americans are very obsessed with race. Okay, so no judgment there, but this example is showing Chicago, the city of Chicago in 1940 and in 1960. And this is a map of the people living in Chicago. The yellow parts, yellow-orange parts, but where you have less than 1/4 African Americans, okay, which you could say are black people, I guess. And the darker parts, brown black, are more than 75% African Americans. So you can see in 1940, the African Americans tend to live kind of together. Not always, huh? There's all places a little bit separated. Like up there, it's kind of mixed. It's better. Down here, it's kind of very separated, segregated. Here in 1960, you can see that the neighborhoods with African Americans have grown, and it's still pretty segregated, and there's no forcing here. This is the people themselves deciding, buying a house, deciding where they want to live, okay? You can see the north part of Chicago up there is a little bit more mixed, but in the south it's pretty segregated. So there's also a geographical segregation. So you can see how characteristics determine the similarities. Okay? Okay, just to give you some understanding. And this, in sociology, people see there's actually two ways for people to look like each other. They are called selection and social influence. Okay? It's from sociology. Selection is, I decide who I'm going to be friends with, so it's internal. I decide. Okay? So individuals drive the formation. But the other one is coming from the outside, social influence. I am in a place, and I see the people around me, and I want to be like them. Okay? So I change my behavior to be like them. That's called peer pressure also. And so that's an external mechanism. And both of these are pushing, defining how people become friends. Okay? So they're kind of very hard to understand. It's all happening inside people's heads. So how are we going to do that? We're going to use the technique we do throughout the course. We're going to bring these things inside the graph. We're going to bring these mechanisms in the graph so we can use graph theory to reason about human psychology. So this is why we will have these focus nodes, and this is called affiliation networks. Okay, so we'll see an example of that. But if you study sociology, so this is partly a course on sociology, selection and social influence, it's kind of very complicated. Okay? And you have to follow it over time. You have to see what happens, like in Chicago, over the time, how it evolves. Things are always changing in the real world and in the internet. And this is called longitudinal studies. All that means is you're studying it over time. Okay? Teenagers tend to be similar to each other. They seek out people like them, that's selection, but they also have pressure to conform, that's social influence. Okay? You have to distinguish. Let's say you want to reduce the use of illicit drugs, bad drugs. Okay? That will only work really well if the drug use is coming from social influence. Okay? Otherwise, it will only target the people, it will only affect the people it targets directly. Otherwise, social influence, you can influence everybody. In the selection, it's the people themselves who decide. Okay? So if they decide to not use the drugs, they will change their social circles. But people who are, where it's coming from social influence will not be affected. So you have to make kind of understand the two. Okay, so that gives you kind of some intuition, huh? Selection and social influence, kind of complicated things. Now we go back and we will bring it kind of as into the network, make it kind of formal. We want to bring this similarity stuff, this homophoby, into the graph. We want to add it, so we want to kind of define an extended graph so we can reason on the graph structure. We will define an extended graph. And once we have that, we can study the network evolution purely like in graph theory, which is nice. Okay? So that's what we're going to do. So we're going to define affiliation networks. We have focus nodes, which means the similarity goes in the graph. Then we're going to measure it, how it works. We're going to have networks where we have both people and focus nodes. So we have many kinds of closure, and then also the big real-world data. So we're going to really see how these networks evolve. Okay, so here's the basic idea. We're going to show individuals, the people, and what they do. So we add these new nodes, these rectangles, which are called focus nodes, focus or foci. This is a bipartite graph. So a bipartite graph means you can separate the nodes into two groups, and each edge connects a node from one group to the other. So each person is having some activities. So Daniel is in the karate club, and Anna is in the literacy club and in the karate club. Okay? And so this shows what these people, what their interests are. And now we can use it to kind of look at similarity. Here's another kind of example. It's a nice one because it kind of connects to the internet and these big things. Here we have 5 big companies: Amazon, Google, Apple, Disney, and General Electric. And the network shows the corporate boards. So each big company has a board of directors, which kind of who gives advice on how what the company should do, the strategy. So you can see this guy, Al Gore. You may have heard of this guy. He used to be vice president of the United States. He's on the board of Apple. Okay? And you see this person, Andre Young, is on the boards of Apple and General Electric. That's kind of weird because General Electric is doing electrical stuff and Apple is computers. But computers are electrical, okay? And look at this guy, you may have heard of him, Steve Jobs. So this was in 2009 now. He was still active in those days. He's in Apple and Disney. That's kind of weird, huh? What does Apple have to do with Disney? Well, a lot, actually. So Steve Jobs started in Apple, but then he was in Pixar, and they were bought by Disney. So he's doing media. He was doing media and computers. So you can see that computers and media are somehow connected, because you have this guy which is both. Okay? So Apple is moving toward media activities. You can deduce it from this graph. Okay? So you see the graph is very useful. It gives you lots of information. Okay, let's see how to measure it now. So we have a graph. Is it true in this graph that people who are like each other are more likely to be friends or not? Is it true that people who are similar, who have the same focus nodes, will be friends? That's something you can actually test. Are similar nodes more likely to be connected? So here's an example. This is a classroom in a primary school, so a very low grade, with boys and girls. So the boys are the white circles and the girls are the gray circles. And the line is when there's friends. When they're friends. And you can see they're kind of friends between each other, but not everybody, they're friends, some of them. And the question, is there homophily? That means, does the fact, are two boys more likely to be friends, or two girls, than friendship between boy and girl? Okay. Is it true that boys tend to be friends with boys and girls with girls? So that's actually something you can test. Because we can do statistics. So homophily is not just something you accept, you can test it. Here's one way to test it. Let's say you have, we're going to test it for this network. The fraction P are boys and Q are girls. So P plus Q is equal to 1. If there's no homophily, if everything is completely uniform, then we would expect boy-boy edges to be randomly connected between the fraction P and the fraction P, so P squared, and Q squared, which would be girl-girl edges, and 2 times PQ would be boy-girl edges, because it can be boy-girl and girl-boy. So we can actually test for homophily. If the fraction of boy-girl edges is significantly less than 2 times PQ, that means there's not so many boy-girl friendships, they're mostly boy-boy and girl-girl, then there is homophily, okay? So in this example, we have 9 nodes, 6 boys and 3 girls, so there's 2/3 boys, 1/3 girls, so 2PQ would be 8/18ths. And now you can actually count the number of edges, boy-girl edges in here, and you can see that the actual fraction is 5/18ths. So it seems to be less. Okay, it seems to be less. So that maybe there's homophily here. Okay, seems to be different. But is it different? So you have done statistics, right? Do you remember your statistics course? There's something called student t-test. Do you remember that? Yes. Well, actually, student t-test is a test that you can use to check whether the samples are significantly different from the means. Okay. So you can use student t-test on this, and you can because of course there can be fluctuations. So it's really hard to know whether it's really significant. So you have to do some kind of test. And you can see that 5/18ths is inside the 95% confidence interval. So actually, it's kind of on the edge. So 5/18ths is still not really sure that it's no homophily. I mean that there is homophily, but still probably there is, because we're like at the 95% confidence. Okay. So you see, you can use statistics. This is just a connection on statistics. Okay. Okay. So we have these social affiliation networks now. We will take affiliation network. So this is an affiliation network. Bipartite. And we will merge it with the social network. Okay. We will take the social network, we have all the people in the friend nodes, and we'll add these focus nodes. Okay? And then both of the networks evolve. So you have something called co-evolution. Maybe people will become a member of the karate club. So you have new nodes, people edges to the focus, Or two people become friends because they are both members of the chess club or something. So you have two kinds of edges, person, and person focus. Okay? So the example we saw before is a social affiliation network. This is the primary school with boys and girls, because boy and girl are like focus nodes. And so each of these nodes, now all the nodes will be just simple white circles, and each node is either a member of the boy group or a member of the girl group. So there's two foci here, boy and girl. So the example we showed is already a social affiliation network. Okay. So now we have actually more closure. Things get richer. We have this new extra kind of node called a focus node. So we have more than just triadic closure. So we have three kinds of closure now. So now we have a more sophisticated way of seeing what happens. At the top, Bill and Carl become friends because they have a common friend, Anna. That's triadic closure. But in the second one, Bill and Carl become friends because they both are a member of the airplane club. Whatever, okay, role-playing game club. Or they're both a member of the throw all your smartphone in the garbage club or something. So they become friends. But then you have this is also becoming friends. We have a new kind of closure too. So Anna is in the chess club, and Bill is friend with Anna. So Bill says, hey, maybe I also join the chess club, okay? So this is called membership closure. So now we have three kinds of closure, three ways this network can evolve. It's more complicated, but it gives us more insight. It's called triadic closure, focal closure, and membership closure. And here's an example that we can look at. So we have our trusty karate club here, and several people are members, Bob, Anna, Daniel, and Frank. We also have another people who are literacy volunteers. They will help people to learn how to read, whatever. So Anna, Grace, and Frank are there. So this network will evolve over time. Okay? But now we can actually predict it. We actually can understand. Remember last week we had a karate club where you had two people who had lots of friends, and you could actually predict that maybe the club would split. Here you can also predict, and you can predict more things. So for example, somebody like Esther here is not in the karate club, but Esther is a friend of Bob, so maybe Esther will join the karate club someday. But it's less likely that Esther joins literacy volunteers. Maybe she will still do it. It's not telling you all the information. It just gives the trends, okay? Or Bob and Daniel are both in karate club, and they are not friends, but maybe they become friends. But they also have a common friend, Anna. So there's like two reasons now for them to become friends. They have a common friend, Anna, and they're in the karate club. So it's pretty likely, there's a good chance that they will become friends. Okay? And so on. So maybe Claire will join literacy volunteers. So you can see that the social affiliation lets you kind of predict what's going to happen. Very important. Okay, so that's kind of the theory. There's some empirical studies now. So this is all kind of theory now, what I'm telling you. Is it really like that? Well, there were some studies. So I'll show you some theory studies for the three kinds of closure: triadic, focal, membership. So first of all, let's look at triadic closure. This is a simple one. Friends of friends become friends. how much more likely is an edge to form between two people if they have more friends in common? So you think two people, the more friends they have in common, the more chance they have to become friends. So people study this. So you take a network, a real world network, take snapshots, okay? And for every number k, you identify all the pairs of friends who have exactly k friends in common. And maybe they have 3 friends in common, but they're not friends yet. Okay? Okay? And in the second snapshot, some of those will connect. So tk will be the fraction of those pairs that have connected. So this is also something you can compute. So this is a study done by 2 researchers called Kosinitz and Watts. This is 22,000 university students at a large university in America of email. So university students are very common guinea pigs, you guys. So they took some university and they studied that. And they computed the email. So if 2 people communicate by email, 2 people are friends if they communicate in the past 60 days. Otherwise, they're not friends, and they make a snapshot per day. And then you can make a graph. Okay? Because each time you do the next snapshot, you see some fraction become friends. So TK is the probability that 2 people form a link per day if they have K common friends. Okay? So here's the common friends, so this is the K. And here's the probability per day. So it's kind of low, but of course it accumulates. This is just every day, so it's going to be small. But still, it's going to keep going like that. So what happens? If you look, this is the actual graph. Look what happens. If people have 0 friends, then they don't become friends. If they have, very funny, if they have 1 friend, they have a little bit. If they have 2 friends, 3 friends, 4, the probability increases. And it's kind of linear up to 8 friends. And then it goes even more than linear. So if you have more than 8 friends, you're pretty likely to become friends. So this is really good evidence. You know, it's a funny thing here. 1 friend is not enough. 0, if you have 1 friend in common, it doesn't change anything, but it only really starts going up once you have 2 friends. That's weird, huh? Why is that? Who knows? Ask the psychologists. So it's not enough to have 1 friend, but if you have 2, it goes up. And then the more it goes up, and we can actually make a theoretical model of this. So this kind of is like a straight line, but it's not really a straight line. So we can make a theoretical model, and this gives us 2 straight lines. So I'll show you in the next slide. If one straight line is 1 minus p to the k, and this is 1 minus p to the k minus 1. So you can make a theoretical model. That's a good way to understand things. You see the graph, and then you try to figure out how is it possible. So you make a model. So the idea is, suppose that each common friend gives an independent probability of forming per day. That means each friend has like separate influence, and they're independent, they're not connected. Okay? So 2 people with K common friends will link. So with P to the K will be for K, but fail to link, that means there's no connection, because each of the friends will cause a connection. So each one succeeds with probability P. So each one fails with probability 1 minus p. And if you have k friends, and they're independent, then you can multiply the probabilities. Okay? So this gives 1 minus p to the k, for k friends. At least one link forms is 1 minus this. This is they fail to link, yeah? So there's 0 links. So the 1 minus that is at least one link. Is 1 minus p to the k. So this gives you the upward dotted line. So it's kind of true. Up to 8 friends, each friend has independent influence. But actually, there's this weird thing. So actually, the first friend has no influence. It only starts with the second friend. So the better model is 1 minus p to the k minus 1. But then it kind of grows a little bit faster. So this first friend doesn't have much influence. It really only starts with 2. And it's kind of linear, but it's a little bit more than linear. But it works pretty well, you see? So each friend has kind of independent influence. You see that? So that's a good evidence for triadic closure. Okay? So this is like real world evidence. So here's the second one now, which is focal closure. Okay? So this is students taking classes. And the focus is the class, the course. 2 students share focus if they're in the same class. It's a very simple thing that you can work and study. So again, you can see what happens. The number of common foci is how many classes they have in common. Okay, so 0 classes in common don't know each other. It's almost 0. But if they have 1 class in common, they will become friends with some probability. But 2 classes doesn't change much. The first class is the main one. Once they are in a class, it has the effect. So it kind of flattens out. So this is kind of diminishing returns. Okay, so it seems that the important thing is having at least 1 class. It does increase a little bit after that, but like 4 and 5 classes doesn't make it higher. As soon as, it's like you've already got the effect after 1, 2 classes, okay? So this is focal closure. So people in the same class, well, they tend to become friends. It's kind of logical, huh? They will be in the same room, huh? So now let's look at the third one. This is membership closure. Now we're looking at joining a focus, joining a club. Okay? So here you have kind of a social network called LiveJournal, which has things called communities, groups of people that discuss to each other. Okay? So you have people who are members of a community, like maybe you have 10 friends who are members of the, I don't know, the cherry pie lover community. So that's one I'm a member of. Okay, so you have many friends in some community. And what is the probability that if I have 10 friends that are in this community, I will also join? Okay. Well, if the more friends I have that are in there, the stronger the probability is I will join, okay? But it kind of flattens out after a while. If I have 20 friends that are in the hockey puck community, or 45 doesn't make much difference. It kind of flattens out. The probability increases, but sort of flattens out. And again, you can see there's a weird effect where 1 is not enough. It only really starts having an effect with 2. Somehow, when people have 1 friend who's doing something, they don't really care. But as soon as there's 2, ooh, now it's important, okay? Seems to be how people think. 1 is just random, they don't really care. As long as it's more than 2, they will think. Yeah, questions?
Il ne faut pas juste se dire que l'étude n'est pas assez précise pour un ami plutôt que tirer des conclusions comme ça.
Ah, mais les probabilities sont calculées de façon très précise. Hein?
Très très précis.
Ah oui. So the probabilities, there's an error bar here, right? So of course you have some effect that because there's a sample. So you have very large errors here, but for the very small ones, the error bars are very small. Huh? So these probabilities are very precise for this community. Huh? Maybe it doesn't work for Facebook, but for live journal it's precise. Huh? So this is a very precise thing. Here it's less precise. Huh? Here you have, but the effect is not so important either. So there's a lot of fluctuation when it starts flattening out. So you have these error bars. Right? So this vertical bar, this shows you kind of the error. Right? Yeah, but it's a good question, huh? Because once you start doing statistical analysis, you have to worry about how solid is the statistics. Huh? Okay, so you can see that membership closure works. The more friends I have in a club, the more chance I have of joining that club. Okay. And there's also another study of membership closure done for Wikipedia. So now we're talking about not the readers of Wikipedia, we're talking about the editors, the people who write the articles. Okay? There's thousands, many people. Maybe some of you write Wikipedia articles. Okay? The probability of editing a Wikipedia article as function of the number of friends who have edited that article. Okay? So the more friends I have that edit, maybe there's an article on obscure philosophers. I don't know, Plotinus or something. Well, the more friends I have editing Plotinus, the more chance I will be there. I'll also say, hey, I have something to say also about this guy. So the probability goes up. And again, there's a weird effect where one is not enough. You see? This is funny, huh? If I have one friend who's interested in Plotinus, it doesn't really matter if Plotinus, who is this guy? But if I have 5 friends, 2, then maybe there's something there, you know, it's kind of human psychology. 1 is not enough. Has to be at least 2, okay? So that works also for Wikipedia. So you can see the 3 kinds of closure that really exist. The triadic focal membership. So you can really understand how these social networks will evolve. Okay? Okay. Let's try to now be a little bit more precise in the psychology, in the sociology. Remember, I talked about selection and social influence. So far, we didn't say anything about that. Huh? Selection is where I decide, but social influence is where I feel the peer pressure, and I do it because my friends do it, even if I don't really want to. So you have the external and the internal effect. This seems to be very hard, right, to compare. How can you get inside somebody's brain and see how strong is selection compared to social influence? But if you're clever, you can do it. Okay? So there was a study done on comparing them. So these are the 2 sources of homophily, of the similarity. There's the internal one, selection, and the external one, which is called social influence. So either I decide, I don't care what my friends do, or I do it what my friends do. Okay? And it's kind of hard to distinguish them. The focus notes, joining a club. Why did I join the club? Because I want to, or because the social peer pressure? Well, let's see if we can compare them. You can see we're actually now doing real sociology research on the internet. So we have to separate 2 pieces. One where you have mostly selection, so internal choices, and the other one where it's mostly peer pressure. And then we can compare them. Right? It seems to be kind of hard, but there were some clever guys who had figured out how to do it. There was a study of Wikipedia. Wikipedia seems to be a good place to study things. Okay, so everybody knows Wikipedia. We already mentioned Wikipedia, but now we go a little bit more into detail on how it works. Okay, so it's a collaborative encyclopedia. It's a very good, high-quality collaborative encyclopedia written by editors. So let's study the behavior of these editors. Okay, and we have a social network now. So we define a social network, and the nodes are the editors, the redactor, people who write the pages. But editors have articles or pages that they edit, they write or update. But they also have talk pages. So these editors will discuss things with each other, huh? Maybe they're physicists and they have to talk about wave-particle duality, or maybe they're interested in politics and they have to talk about what happened to the British Empire at a certain date or whatever, so they have something to discuss and agree. So they have a talk page. Okay? And so the editors know each other if they actually talk with each other. So two editors editing the same Wikipedia page, they're not necessarily friends, okay? But if they discuss together on the top page, then we can say they're linked, they're kind of like friends, okay? And we can also define how similar these editors are. Two editors that edit exactly the same set of pages, they're like very similar, okay? So we can define the similarity between two editors. So the number of articles edited by both divided by the number of articles edited by at least one. So if you look at it, both would be this little intersection, and at least one would be the bigger one. But if they're kind of really overlapping, this number will be equal to 1. But if they're very separate, the number will be 0. Okay? This is actually the same as neighborhood overlap, what we saw last time. Okay? So we look at two nodes and how common are the neighborhoods. So the pages I edit are like my neighborhood, huh? So this is the similarity. So this is the base. And now we can actually show what happens over time. So this is a very kind of subtle graph, okay? Here we have two editors, and they're editing pages, okay? And at some time, and they start by not knowing each other, and at some point, they start talking to each other, okay? And that point is the 0. So if we have two editors, they may be very similar or not similar. So the similarity is 0. So they start being not so similar. And we normalize it. So at the left of this line, the editors don't know each other. No, they're not friends. And at the right of the line, they are talking directly to each other. They know each other. Okay? And we can compute the similarity. Now this graph actually does the average over a whole bunch of editors. So I talk about 2, but in fact the graph showed the average. Okay? So on the left, they don't know each other. And on the right, they know each other. So on the left, you can see what happens. The similarity increases, and somehow accelerates. The increase in similarity goes way up, and at some point they become so similar that they hit each other. They start talking to each other, but now they start discussing. So each editor will be influenced by the other. So on the left, they don't talk, so it's only internal, so it's only selection, okay? Each editor has their own thought. They don't care what the others, they just do what they do. But on the right, they're talking to each other. So there's the peer pressure. Two physicists are talking, and they kind of agree. So each one is like taking into account the other one. So you have social influence. So you can see on the left, it's mostly selection. And on the right, it starts getting more and more social influence. So you see what happens. When it's only selection, the similarity increases very fast. But as soon as they start talking to each other, the similarities doesn't increase so fast. Well, maybe they divide up the work. One editor says, I will talk about Heisenberg, and the other one says, okay, and I'll talk about Schrödinger. So one of them does Heisenberg, the other one does Schrödinger. So now they become different. They're not so similar anymore, you see, because they decide to divide up the work. So the similarity is going slower on the right. So you can see that the effect of selection and social influence. On the left, it's mostly selection. On the right, we start to have more and more social influence. And the more they talk, the more social influence there is. So then and it seems that they will not become so similar anymore after that. Okay? Okay. So that gives us what I call closure analysis, the three kinds of closure with real data. So the closure is real, it really exists, and you can get models of it, like the interdependence of the friends. But we still don't know so much. So this is not the end of the research. We still only know a little bit about this. Human beings are very complicated, okay? And we still don't really know how they think. Why is the one friend thing so important? Okay? So the analysis of social networks is still early. Maybe people inside Facebook have advanced much more in social network analysis, but they don't tell us. They keep it secret. Okay? So this is one of the things we can study in the project, in the course. Okay? Okay, so let me make a small break now. And after the break, we'll start talking about friends and enemies. So now we will talk about networks with both friends and enemies. And that actually is very important and exists on the internet, but in real life. So up to now, the linked strength is always positive. So how strong the friendship is, close friends and acquaintances. But it's not always like that. Sometimes there's negative effects. Enemies, distrust. Sometimes you don't trust the other person. So the social network becomes a friend-enemy network. So let's study that now. That's very interesting, actually. Now the links can be positive or negative. And there's a tension. Remember, two nodes with a common friend can become friends, right? But two nodes with a common enemy will become friends, or maybe they're enemies, or whatever. So there is something going on there. People will change their opinions, friend, enemy, and so on. And you have also some kind of evolution, and this is called structural balance. There's a kind of balance, equilibrium. So we'll see that. And you can have global consequences. That's actually really neat. So everybody decides, should I be friend or enemy? And it's very local. But globally, it has real consequences. Globally, the network will kind of converge into two groups of friends, and those groups are enemies, or n groups of friends, and those groups are all enemies of each other. And all of that because of the local friend-enemy stuff. Okay, so now we have some real interesting things going on, and I'll show you how it works, and also some real-world examples. Okay, so again, we're going to use the same technique as we did before. I'm going to define a formal model, a simple formal model. We analyze the model, and then we see how it gives us intuition on the network. Okay? We will consider social networks where everybody knows everybody. So previously, two nodes, maybe they don't know each other, so there's no link. But now there's always a link, okay? Because we have plus or minus, so everybody has an opinion on everybody else. Well, so if I have four nodes, here, four nodes, there will be links between all of them, and all of these will have plus or minus attached, okay? A, B, C, D. This is called a complete graph, okay? A complete graph is a graph where there's an edge joining every pair of nodes. So all nodes know about each other and have an opinion, plus or minus. So if we assume this, it's not neutral, okay? There's not a node which is neutral. They all have opinions. This is also called a clique. Clique and complete graph, those are the technical terms. This is in terms of graph theory, a clique or complete graph. So, and each edge is labeled with a plus or a minus. And we're going to assume only that. I mean, it could be strong enemy or weak enemy. Well, we'll leave that for later, but here it'll just be plus or minus. So this is called a labeled complete graph, okay? No pair of people is indifferent or unaware. All pairs are either friends or enemies, okay? So this is actually a reasonable model, because there are many groups where it's like this. A classroom, a small company, everybody knows everybody. A boardroom of directors, everybody knows everybody. A sports team, everybody knows everybody. International relations, every country has relationships with every other country. So it's actually a reasonable to look at complete graph. Okay. Now we're going to look at the stress of becoming friend or enemy, and we're going to look at three triangles. Okay, so we have three people, A, B, C. So B and C are friends, but B and A are enemies. What about A and C? Okay, so we have this notion of balance. Balance is kind of like a stable situation. Unbalanced is kind of unstable, and maybe things are going to change. Okay, so if we have a minus here, then B and C are friends, and they have a common enemy, A. That's reasonable, huh? They are agreeing with each other. But you can also have an unbalanced situation. Something like this. So, C is friends with B, C is friends with A, but A and B are enemies. C has two friends, and they're enemies. So the next time C has a party, C will invite A and B, and A and B, what do? They start arguing, and they start fighting each other, or whatever, okay? That's not very stable. So this situation is kind of unstable, unbalanced. But this one is kind of stable. You see, so with enemies, you have to be careful. Sometimes it's stable or unstable. And so for our formal model, we're going to look at all the possibilities. Okay? So this is a simplified model of the real world, but still it's kind of interesting. Here we have three people, A, B, C. In the left, they're all friends, plus, plus, plus. That's very stable. Three people, they're very happy, okay? Or here you have B and C are friends, and they have a common enemy. That's also pretty stable, okay? You have this common enemy, the bad guy. So I'm not sure. Let's say I'm thinking of superhero movies, okay? Iron Man and Doctor Strange. I guess they're friends, right? Well, we'll assume they're friends, but Thanos is the enemy, okay? So that's kind of a situation. That's stable. Now we have other situations. Let's say we have minus, minus, minus. Everybody's enemy with everybody else. That's pretty stressed, okay? That's kind of a stressful situation. Or we have A is friends with B and with C, but B and C are enemies. That's not very stable either. Here, these three are always going to be antagonistic, and here, BC, there's a conflict kind of there, because BC are both liking A, but they hate each other or something, So there's four possible configurations. We say two of them are balanced, so this is natural. This is something which is kind of stable and can go on since it exists. And two of them are kind of stressed out, unbalanced, okay? Coming from psychology. So a triangle is balanced if it is plus, 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 or plus, minus, minus, okay? A triangle is unbalanced if it's minus, 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 or plus, plus, minus. Okay, that's simple formal model, okay? And now we can define so we have this definition for triangles. Now we can look at the whole graph. The whole graph is balanced if for every triangle in the graph, it's plus, 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 or plus, minus, minus. So every triangle is balanced. The example is not there, but the example, there's many examples, and I can draw an example on the board. So if I have, for example, A, B, C, D, so there's connections between the two. So let's say we have plus, minus, minus, so we have minus, minus here, and there's a plus here, okay, and we have minus and a plus, and a plus. So we have plus, minus, minus, we have plus, 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 we have plus, minus, minus, okay, and if you look at the other ones, here's another plus, minus, minus, so there's actually and plus, minus, minus, and plus, minus, minus. So there's four triangles here, and they're all balanced. One of them is plus, 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 the other three are plus, minus, minus. So this is a balanced graph. Okay? But of course we can make it unbalanced very easily. Okay? So let's say I have minus, minus, minus again. But here I put a minus. And plus, plus, minus. Okay, so here we have minus, minus, minus. That's not balanced. Okay? Here we have plus, plus, minus. That's not balanced. We have two common friends and they're enemies. A and C are enemies, but they're both friends of D. So this one is unbalanced. Okay? Okay, so we can talk about the whole graph being balanced or unbalanced. Okay? So this is a local definition. So I'm going to make the difference between local definition and global definition. So local definition is a definition where I'm talking about all the little triangles. Okay? For all the triangles, they're balanced. All the triangles, they're not all balanced. Some of them are unbalanced. Okay? So that's a local definition. But can we say something about the overall structure of this? What is actually going on here? We are looking at the individuals, but is there some overall big picture? So the question, is there like a global way of looking at balance? And the answer is yes, a very interesting global way. And this is the following. It's actually a theorem, the structural balance theorem, and it says the following. If a labeled complete graph is balanced, then there's two possibilities. Everybody's friends, that's one possibility, or you can divide all the nodes in two groups. So all the nodes are inside this set in here, and there's connections between. And inside the group, it's only friends. Inside the group, there's friends, and the two groups are enemies with each other. All the X people are enemies of the Y people. You see? It's very interesting, huh? We take a local property, which is little balanced triangles, and now we have an overall global structure of the whole thing. So if the graph is balanced, then we have this. If it's not balanced, we don't have this. But in fact, the not balanced graph is kind of stressed. So what's going to happen is the not balanced graph will be slowly evolving to become balanced. So for example, if I have the plus, plus, minus case, remember? B and C are enemies, but they have common friend A. So this is kind of an unbalanced. But in real life, something like this will not stay forever. It's unstable. Something's going to happen here. Either B and C will become friends, and this will become a plus, or A will decide B will not like A anymore and become enemies with A, so you have the plus, minus, minus. So something is going to happen. So what that means is that in real life, things are going to evolve toward this. That means in a real life situation, what you're going to have is approximately this. And all the unstable triangles, which are not fitting in this, they're kind of stressed and they're going to be changing. So if you have a balanced definition of balance, the world is going to evolve like this. Eventually you're going to have a whole bunch of friends and a whole bunch of friends, and they're hating each other's guts. Okay? So that is the balance theorem. So it says, if you have the local structure, then you can prove the global structure. This was proved in 1953 by a famous graph theoretician called Frank Harari. So this is called the balance theorem. And we are going to prove it. I want to prove it for you. Now, I want to reason about this. It's nice. It's a very nice proof, actually. So suppose we have a labeled complete graph and it's balanced. Remember what that means, huh? It means plus, 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 or plus, minus, minus. Okay? And now we want to show that we have two groups. Question?
Yes. Does this theorem apply to more than two sets? Can it apply to 3, 4, 5 group of people?
In this theorem, you will always have two groups, not more.
Okay.
But we will see a slightly different one called weak balance, where you have n groups. So just be patient and we get to the end. So the This is actually strong balance. But if you make the balance a little bit weaker, you can have n groups. But first, let's do this one. See how it works. Okay. Here you have plus, 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 and plus, minus, minus. Okay. So let's prove it now. Be careful when you prove this. In previous edition of the course, when I can ask for this proof on the exam. Somehow people don't understand that the proof has a direction. If something, then something. Sometimes people have proved the opposite thing for me. They've proved that if you have this, then the triangles are balanced. Oh, that's very easy, okay? That's not what I'm doing. I'm going the hard way, okay? The hard way is, if you have all the little triangles are balanced, then the big structure is that. That's what I'm going to prove. So be careful about the direction, huh? Proofs are directional, okay? So we're going to prove it now. And you see, it's not that hard if you do it right. So we assume it's balanced. So remember the definition of balance? Plus, 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 or plus, minus, minus. Okay? So we have the labeled complete graph is balanced. Is balanced. We have plus, plus, plus for all the triangles, or plus, minus, minus. So that's all, nothing else. Now we will prove that we have two groups that are against each other. Okay, so there's two parts of it. First of all, if all of the links are plus, 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 then there's only one. In fact, if you look carefully, there's actually two possibilities. If there's no negative links, then you only have one group and everybody is friends. Everybody. That's easy, okay? So we'll assume that there's at least one negative link. Okay? So how do we prove it? Well, very nice. We try to make some structure. So we pick a node of the graph. And pick a node, A. And we'll study the graph from the viewpoint of A. Okay? Now, we will define two sets of nodes. X will be A plus all the friends of A. We can define that. And Y will be the enemies of A. So we can define that, and that's not doing anything special. Well, this is X. So we know that there's some node B, and there's maybe many others, which is a friend of A. And then there's the Y. And Y contains nodes which are enemy. So this is all we're assuming, huh? X will be A plus all the friends. Maybe there's another one here, B. And Y is all the enemies, okay, of A. Now, the question. We have defined X and Y. Do these X and Y satisfy the theorem? Are they the same as these X and Y? Actually, they do. We can prove that. We have to prove three things. Every two nodes in X are friends. So we have to prove that D and B are friends. We have to prove that every two nodes in Y are friends. We have to prove that C and E are friends. And we have to prove that every node in X is an enemy of every node in Y. And then we're good. You see that? You see how the reasoning works? We define X and Y in a simple way, and then we can actually show that these are the good X and Y, and we will use the balanced property to prove that. Okay? Let us make a diagram. I will make the diagram on the board. Okay? We will examine each of the three properties, and then we're done. QED. It's simple, right? Well, I make the diagram here. First of all, B and D. So B and D. Are they friends or enemies? What is written on this link, BD? Well, we can actually figure it out, huh? The only possible triangles are plus, 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 and plus, minus, minus. So we have already two pluses. So it's clear we cannot have this. It has to be this. You see that? It has to be this. Because we are assuming that we have a labeled complete graph. So we only have these two triangles. So that means we have proved the first thing. All nodes in X are friends of each other. What about C and E? What is the polarity on there? Well, we already have two minuses. We have two minuses. There's only one possibility, huh? It has to be a plus. See that? So C and E are clearly friends. What about B and E? Well, if you look at B and E, there is a plus on this triangle here. B, A, E. There is a plus and a minus. What does this link have to be? Because we have a labeled graph, it has to be
minus.
Minus, exactly. So that means B and E are enemies. And the same for any node connecting an X and a Y. So we have proved that all the nodes in X are friends mutually, all the nodes in Y are friends, and they're enemies between. We've proved it. You see how easy it is. And that's how this guy Harari makes a living, huh? But he proved, of course, things much more general than this. Huh? This is a simple example. So we have this very nice theorem. This actually has a lot of applications. So here's one application. This one is international relations. Okay. In 1972, there was a conflict between the separation of Bangladesh and Pakistan. Of course, you know all about this, so I'm not just giving you this news here. In those days, there existed something called USSR. Remember USSR? Probably disappeared before you were born, but I remember. Huh? See how old I am. USSR and China were enemies. China and India were enemies. India and Pakistan were enemies. And we're assuming strong balance here. The USA wanted to improve relations with China. It wanted to be friend with China. So it supported the enemies of China's enemies. So Pakistan is an enemy of an enemy of China, so it supported Pakistan. You see how naive sometimes politics are. North Vietnam became friendly toward India. Okay? Pakistan severed relations with the Eastern Bloc countries. So Eastern Bloc countries are friends of USSR. They recognize Bangladesh. Okay? And China vetoed the acceptance of Bangladesh in the United Nations. All of these can be deduced from the balance theorem. So you see, sometimes politics is easy. Here's another example, World War I. So now, remember your history courses. I don't know if you remember your history courses. I will refresh your memory. Okay? From 1872, this is little a, to 1881, there was something called the Three Emperors League, la Ligue des Trois Empereurs. Do you remember that? Does it ring a bell? Well, Russia, Austria, Hungary. Do you remember Austria-Hungary? That was a thing. It was an empire, and the Emperor of Germany were leaguing. Okay, and then in B, something called the Triple Alliance was formed in 1882 between Italy, Austria-Hungary, and Germany. In C, it was something called the German-Russian lapse, the lapsus Germano-Russe in 1890, where there was a treaty between Germany and Russia, and it was allowed to lapse. So So Germany was no longer allied to Russia, and Austria-Hungary neither also let it drop. In 1891 to 1994, there was a Franco-Russian alliance was formed. You see how these empires love to play games. And in 1904, there was something called the Entente Cordiale. Cordiale, it means between historical enemies, France and Great Britain. They made kind of an alliance, an entente. Okay? And in F, there was also then a British-Russian alliance. Now look at the situation. You have 3 allied countries and 3 allied, and these are enemies. What happened then? Something called World War I happened after this. Okay, so you can see at some point you have 2 blocks opposing alliances. And so you kind of have a slide into an antagonistic situation. And the structural balance actually helps explain that. Because the weakly balanced triangles have a tendency to disappear. Okay? Let me now make a third example. Now we go to internet. User communities on the web. Sometimes it's possible to dislike. Of course, Facebook doesn't dislike because it's sort of negative. Disliking, it's only liking, right? But you can also dislike things. Trust and distrust, okay? Distrust and dislike. But it's not so simple. It's not so simple here because the negative relationship is not always so simple. First of all, is it commutative? If A dislikes B, does B dislike A? Sometimes it is, sometimes not. Is it transitive? A trusts B, B trusts C. Does A trust C? Sometimes. Okay. Is the distrust is not necessarily transitive. A distrusts B, B distrusts C. What about A and C? Maybe A will trust C, or maybe not. If distrust is like being an enemy, then the enemies of my enemies are my friends. Okay? But if distrust is like believing the other guy is an idiot, then it's not going to be transitive. If A thinks that B is a moron, and B thinks that C is a moron, it's not because B thinks that C is a moron that A is going to think otherwise. A will probably think that all these guys are morons, okay? So distrust is more complicated, okay? There's something called opinions, where trust is sort of like political alignment. So you can say A trusts C, it's like plausible. But a website that rates products. So if I have expertise, if B judges something, and A thinks that B is a moron, not an expert, expertise, then A will probably not trust C either. Okay? So the conclusion is, on the web, you have to be very careful. You're not always going to be like structural balance. Sometimes it's more complicated than that. You have to look at the model and figure out what's going on. Okay? And this is interesting because now I want to go to something a little bit more subtle than structural balance. I want now to talk about a variation called weak structural balance. Okay? Here, which is a thing, and sometimes it's a very reasonable way of looking at things. So the moral is, when you define a formal model, be very careful that the model applies to reality. Okay? Sometimes structural balance applies, sometimes it doesn't. So now I'm going to define a slightly different kind of structural balance. We're going to change our view of what balance means. Okay? Okay? So remember, we had two bad little triangles. So we had plus, plus, minus, and we had minus, minus, minus. These were the two unbalanced ones. Plus, plus, minus is a person with two friends who do not get along. Okay, who are enemies. A, B, and C, plus, plus, minus. B and C are enemies, but they're both friends with A. Well, maybe that can change. B and C could get reconciled, they could become friends. Okay, B and C might change their opinion. So plus, plus, minus is kind of something that will be unstable, okay? But minus, minus, minus is not the same. Minus, minus, minus is not the same thing. All three are enemies. Okay? This is bad. They hate, all three hate each other, okay? Somehow they're all competitors, for example. Well, this is not likely to change. Whereas the plus, plus, minus can go away. It's very easy for this to go away, and it's very natural to go away. The minus, minus, minus is not going to go away. Okay? So the minus, minus, minus triangles is like a bad situation that's not going to change. So these kind of things are kind of stable. Okay? So we can assume the minus, minus, minus triangles, yeah, they can happen. Question?
Is the only mutation possible for the plus, plus, minus triangle to become a plus, plus?
Oh no, it can also be that B becomes enemy with A, and then you have two friends with a common enemy. That's okay. So, but only one change is enough to turn it stable. So the plus, plus, minus is kind of an unstable, but it's actually easy to fix. Whereas minus, minus, minus is kind of a stable kind of badness. It's not so easy to fix, okay? It's not so easy to fix, yeah? It's, all three are enemies, so that maybe will stay. So we will make now a variation in our model. We will say a labeled complete graph is weakly balanced, not balanced, weakly balanced. We allow plus, 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 minus, minus, and minus, minus, minus. So these are the two we allowed already, but we allow also the minus, minus, minus. Okay? So remember we had balanced, but now we have weakly balanced. So balanced, that was plus, 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 and plus, minus, minus. So basically, two friends with a common enemy, or all friends. But now we allow weakly balanced, where we allow these three again, these two. But we also allow this one. We allow three enemies. We allow this minus, minus, minus triangle to exist. But the plus, plus, minus, we don't allow it because it tends to go away. Okay? Okay, if we do this, we can have another theorem. And now we have a very interesting global situation. If we look at what the theorem is now, if a labeled complete graph is weakly balanced, then we can divide its nodes into groups. But now we have n groups, not two, any number, some number of groups, and the nodes inside the group are friends, and the nodes between any two groups are enemies. So we have n enemies now, instead of two. So allowing minus, 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 So if this is a thing, if this can exist, the two groups becomes n. It's kind of interesting, huh? So if your situation allows this, you will have n groups and not two. I want to prove this also. It's very interesting to prove because we have this funny n. We don't know n, okay? How can we prove this? Turns out the proof is not that hard. The proof uses recursion because we don't know the value of n. So the n will kind of appear during the proof. We will construct a group, x, and then somehow we will remove its nodes, and then we keep going until we run out of nodes, and somehow we will have n groups. Okay? So again, we will pick, nothing to be known proof. So we pick a node A, and all its friends. We just do that. A and all its friends, and call it x. So what do we need to show? We need to show that all the nodes in X are mutual friends. So A, all the nodes in X are friends of A. But we have to show that they are also mutual friends to each other. So the B and C should be friends. And we also show that they are enemies with all the other nodes. So here are the other nodes. Somehow we have to show that all of these nodes are somehow enemies, okay, of all of these. That's what we have to show. And then we can apply recursion. Then we remove these nodes and we continue with this. And so we peel off one group after the other. See how it works? Then we remove X from the graph. And we have all these nodes left, okay? This set of nodes is strictly smaller in number than the original because we have at least removed one node here, which is A. Huh? So if this is empty, we're done. If it's not empty, we continue. We pick another node A inside here, and we keep going. So we're like peeling off groups. And notice that all these are enemies with X. So we will make all these mutual enemies. Okay? See how it works? Well, we have to do it now. Huh? First of all, we have this. First of all, so B and C are both friends with A. What is their relationship between themselves, B and C? Because we have only these three triangles over alpha. It has to be plus, huh? Why? It has to be plus. Why does it have to be plus? Because we have two pluses. And
the only solution is to have three pluses?
Yes, because the only possible triangle with two pluses is one that has three pluses. So this has to be a plus. Because all the triangles are here. Okay? What about this node? Let me call it D. Okay? This node, D. So, and there's also, so this node D, what is the connection here? So A and D, first of all, what is the connection between A and D?
No.
X is all the nodes that are friends of A.
No.
So D is not a friend of A, right? Right?
Right.
So this has to be
Minus.
minus. So we have, what is between B and D now? We have A, B, D. We have a plus and a minus.
Minus.
What does this have to be?
Minus.
Minus, because the only triangle with both a plus and a minus, the third one is also a minus. So this has to be minus. So we have not proved that all the nodes of X are mutual friends, and all of these are enemies with all of these. We didn't prove anything between these, you don't have to. Now we remove all this. This gives one group. We start over with this set. This set, either it's empty or it's not. If it's not empty, we pick a node, we call it A, and we keep going. You see that? And so we will recursively create, peel off groups, X1, X2, X3. Each one is enemy with all of the succeeding ones, and they're all mutual friends inside. So we have a partition of the original graph into n nodes that satisfy the theorem. Notice that the n is not known in advance here. This is a recursive argument. You see that? It's very elegant, right? Right? You agree it's elegant, huh? So we have now proved that we have n groups. Okay, now we reached almost the end. I made kind of a little summary here. So we have our simple formal model here. It doesn't always apply, but we have different cases. If we have only plus, 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 this is like a social network with triadic closure. We only have one group, everybody's friends, the world is beautiful, okay? But if we have also plus, minus, minus, then we actually have our structural balance theorem says we have two groups. And if we allow also this one, if we allow mutual enemies, three-way, then actually we have n groups. And inside each group, it's only friends. It's funny, it's a strong condition, huh? So these are very interesting cases, huh? And you can also show that the real world is going to evolve toward one of these. Huh? So, of course, it's never going to be perfect, huh? But they will be trending like towards this or this. So if the minus, minus, minus is a thing, then you will have many groups. But if minus, minus, minus is not a thing, then you will have two groups, okay? And of course, if you have all possibilities, then there's nothing. It's a mess, okay? It's interesting, right? So that gives kind of an idea how friend-enemies can evolve. Friend-enemy networks, we show two things. Either the strong structural balance or the weak structural balance. The strong structural balance, you have two big enemy groups. Okay? This was what happened in World War II, in a sense. The Axis and the Allies, the Axis were all friends with each other. There were no triple friends. And the Allies were all friends. Even the USSR and UK and USA were all friends, at least during the war. Huh? So you had two enemy groups. But the weak structural balance is something when you don't have this major world war. This is more like the usual situation. You have enemy groups, and you can have lots of enemies, many enemies, all over, triple enemies. And some situations it's really like this. If you have a sports tournament where you have 10 participating teams, they are always, then you have this situation, huh? Okay. So that's nice, right? Okay. So let me end there. So now you have some intuition on how social networks evolve, huh? And you can apply it in the real world and become very rich. Don't forget me when you become rich. Huh? Give me a percentage. Okay. So let me stop there.